So first of all, let me once more thank the organizers for saving this event and for moving it to the virtual world. It's a very nice opportunity to be here. Also, I'm really glad to see that all our session consists of SSPDs. It's really nice to see that this technology is developing, and I hope to see even better results in the forthcoming years. And now I will switch to my talk, if everyone can hear me and see me well. So my talk today will be about our practical results on developing low noise, ultra low noise, and high efficiency superconducting single photon detector system for telecom range. Basically, I will start with the APDs. All we know that APDs have their plus sides. They basically compact and really ready to use, just plug and play. They also pretty cheap because they do not require any equipment, but they also have downsides like limited system detection efficiency, operating range, and the dark counts are not so great. But like we speak today, we have a rival for the APDs. It's superconductor-based detectors, the SSPDs. We have different types of superconductor-based detectors, but today I will talk about only about SSPDs, also referred to as SNSPDs. So first speaker told really nicely about the basics of SSPDs, but I will just add a few more details. First of all, the SSPDs operate at the temperatures well above the critical temperature of a given superconductor. Also, they have really wide operation range from ultraviolet to mid-infrared. They typically couple to the single mode fibers, but we see that there are more and more works coupling these detectors to the multimode fibers as well, and also creating some kind of single photon cameras, the imagers that work in the free space as well. So another cool features of SSPDs, it's their photon number resolution, like the first speaker told us today again, and they also could be coupled to the waveguides. This was described earlier as well. So at the moment, the record values for the SSPDs are the about 95% system detection efficiency at 1.5. It's 10 to minus 4 dark counts per second. And it's 3 picosecond timing resolution. And important thing that all these values are achieved on different devices. And what we trying to do for the last 5 years, I would say, is to couple all these cool parameters into one device. So at the moment, the different companies sell SSPDs. So every researcher could buy it for their measurements. Here I present just basic characteristics for the SSPDs that are available now. So they have really good system detection efficiency. The dark count rate is fine, but we know that for some implementation in the quantum communication field, we wish the dark counts would be much lower. So we tried to figure out, is it possible to decrease the dark counts in the SSPDs with preserving as high efficiency as we possibly can. So first we analyze what is the origin of the dark counts in the SSPDs. So basically there are two main sources of the dark counts. First source is the black body radiation, it's external source. And I just present here how the dark counts, external dark counts, are changing for different setups, for the free space, for SM telecom fiber, and for banded SM fiber. So basically, these dark counts, external dark counts, they create some kind of a plateau on the dependence of the counting rates versus the bias current of the device. And this is what we wanted to change, basically. Okay, another feature, another source of the dark counts is the intrinsic fluctuations of the superconducting state. So it's a matter of discussion here. So basically, there is an ongoing research on the sources, on the exact nature of the dark counts, and on the photon counts as well. So I will just not stop here for the sake of time saving. Okay, so I've talked about the dark counts. Now I want to talk about the efficiency of the SSPDs. Again, we have several factors that influence the efficiency of SSPD. It's the coupling, the absorption, and the intrinsic efficiency. So at the moment, I think everybody knows how to fix the absorption problem. We just add an optical cavity. Also, almost everyone now can couple the detector, the SSPD, to the fiber really accurately. So the coupling is almost exact. But the really problem here is the intrinsic efficiency of the devices. Basically, we try to figure out how to fix this problem, and we try to fix it using different materials. For example, niobium nitride, which we use here, or niobium titanium nitride, or other different amorphic materials, for example. So yeah, like previous speakers said earlier, there is a potent feature of the SSPDs is the bias current. You always want to send as much current through the detector as you possibly can, just to make the efficiency as high as possible. So basically, the efficiency of the SSPD depends on the photon energy. The higher the photon energy, the simpler it is to detect the photon with SSPD, and also the bias current. So the graph here, it shows that basically for different wavelengths, the dependence of the photon counts on the bias current, it changes shape. We have a plateau region for the shortest wavelengths. And basically what we want to do is to make this plateau for the telecom wavelengths as well. So basically, to improve our results, we try to make the material more disordered. I will switch to the next slide. So like it was showed a couple of years ago, there is a strong correlation between the material disorder, the superconductor disorder, and the efficiency of the SSPDs. Basically, by changing the disorder, you could change this saturation region for a given wavelength at a given temperature. Yeah, so what we try to do here, ideally, we want to concentrate as much energy from a photon in the lowest possible volume of a superconducting strip. And another feature that we try to do is we try to send as much current as we can, like I said. But the limit here is the theoretical depairing current of a superconducting structure that could be calculated, give or take. Yeah. So another important thing to do to achieve better results for the dark counts in SSPDs is to filter out most of the blackbody radiation that comes to the SSPD. So to do it, we have different techniques. Like I showed on the previous slides, there is a technique which is just the bending. You could just bend the fiber and some radiation will filter out. Also, you could always implement different fiber types, which just don't really work at along the wavelengths, but it's not a solution here, as you understand, because we want to have a better result on 1.55. Yeah, so this is actually the slide with our results. So our final result is 76% at 0.6 dark count per second at 1.55. We have similar results for 845 nanometers. What is important here that we already tested the systems in real life experiments. So here I just present a link for the work of our colleagues that were using this system. So basically, in this setup, they used our low noise devices with their trapped ions to create a high efficiency single photon generation system. Here I also show you the graph. It's one of the pioneering works in SSPDs. This is actually the graph that shows this 10 to the minus 4 dark counts per second limit that was obtained, I think, 10 or 15 years ago, something like that. So I just show here this curve of the dark counts versus the bias current. And I also put here a symbol that shows our result. So basically, we're moving towards this low, ultra low dark counts region, and we hopefully will fix it in the nearest future. I also must say that we have also fixed the characteristics at shorter wavelengths. It's not that difficult to increase this efficiency even more with the given dark count rate. So it's actually already 85%. But we're still struggling pushing these results further, but we hopefully will fix it in a coming year or so, because it seems like have a way of increasing this plateau region on the counts versus the bias current dependence. So for those of you who are really interested in technical details, this is actually the photo of a fiber filter that we use in our system to obtain these results that I'm talking about. Maybe it will be interesting for some of you. And this is actually the cryostat that we were using to cool down our detectors. The significant problems with SSPD is the operating temperature. Like I said, it should be really low. But the plus side of the niobium nitride and niobium titanium nitride is the fact that we could operate with the Gifford McMahon cryo coolers. And the cool feature with them, you could just turn it on, and then SSPDs could operate for months or even further with non-stop regime. You just basically detect photons non-stop for this whole month or so. So basically, it's really nice to have these high critical temperature materials for these detectors. But as we see now, it's going by the road of changing this critical temperature. And by changing this critical temperature, it is now possible to move the operating wavelengths of the SSPDs even further. We try to increase the efficiency at telecom range as much as we can. And we usually do it, like I said, by increasing the disorder, but with the disorder, we also decrease the operating temperature. So I think in the future, if nothing will change, we will have to use better cryostats with low operating currents to achieve even better results. So at this point, I will be glad to answer all of your questions, and thank you for your time.